Can I? Oh yeah, that's right. Can't minimize. Okay. Okay, so let's just go over 9 and 10. Even if you then didn't have any issues with these, it's nice working through the logic of them as a class, and then if you want to see how you get graded, things like that, right? Okay, so let's talk about number 9. So problem 3.3 from the book, that was this problem where it's like the lotto just chooses a 4-digit number between 0000 and 9999. You guys remember that? Okay. So now, suppose you have 10 lotteries all doing that thing, number 8. And on a given day, right? So no long time span, just like today. What's the probability there's a match? So let's look at that first. Over here. Okay, so if you're just focusing on one day, there are 10 lotteries running. So it's like having 10 slots, right? And each slot is assigned a number between 0000 and 9999. Did I agree with that? So this is like a classic birthday problem, right? So each lottery, so here's lotto 1, 2, 3, 4, 5. You just find the row of people, and instead of being given a number between 1 and 365, right? They're given a number between 0 and 9999. Did I agree with that? So once you recognize that, this is just a classic birthday problem. It's not, there's no other complementary thing to do with it. You recognize, okay, there are 10 people, 10,000 birthdays, and then you go to that formula. I don't remember what it is, but what comes out of it is something like 0.449%. Okay, anybody have any issues with this one? It's okay, birthday problem? Were you guys on Zoom okay with this one?
Yes.
Yeah.
Okay. So with this one in our pocket, and again, I mean, if you have questions on this, you can ask, right? Were you all able to recognize this as a birthday problem? Good. So with this one in your pocket, the question is, well, how would you move from 9 to 10, where it's like, not today, but now you do this thing here, right? 10 lotteries, choose numbers, and you want to measure if there's a hit or not. But you want to measure if there's a hit just sometime over the course of 20 years. How do you do that? Okay. There are many ways to do it, but let me just show you the quickest way. I get a razor. And we did something very similar in class, but let me just explicate it now. So here's my answer. That's 0.449%. So let me rewrite it like this. 449 over, I think it's over 100,000. Is that 0.449%? I can't actually do the zeros in my head. Let's check. Is it? Okay. Yeah, so what this is saying is like, you know, for every 100,000 times this happens, you're only going to get a hit 449 of those times, right? Did I get that? So now, if you do this thing for 20 years, and it's every weekday, right? So here's weekday 1, weekday 2, weekday 3, weekday 4, and so on, right? There's a lot of weekdays, right? Did I agree with that? There's something like thousands of them. So it's every weekday for 20 years. So you can actually get a count different ways. So I think about it like this, but people have different ways to think about it. So it's 5 days a week, 52 weeks a year, for 20 years. There's one way you could estimate how many weekdays there are, right? And whatever. So you get some count of the number of weekdays. That's what makes slots their own, right? Do you agree with that? Okay, so now for number 10, if you want to know the probability you get a hit sometime, that's really hard to approach directly. So here's where you'd use a complement. You'd say, okay, what's the probability we never exceed, right? We never see this thing, right? So we miss here, we miss here, miss here, miss here, all the way down the line, right? Can I agree with that? Okay, well, the probability of a hit this first time, it's saying, you know, basically if you do this 100,000 times, you'd expect 449 hits. So you can always interpret a probability as a count, right? So here's the probability of a hit. You want to think about misses, though. So here's the number of ways to miss on that first slide. Do I agree with that? There are 449 ways to hit. There are 100,000, take away that, ways to miss. And that's true today, so it's true the next day, the next day, the next day, right? You're going to miss all the way down the line, right? Did I see that? So you're really just taking the complement of that at each slide. But you can always interpret these things as counts, right? Here's a count of what I actually care about. But if I'm going to do the complement, I'll take that out of the overall count. And then I just keep going all the way down the line. So if I do this multiplication-wise all the way down the line, I have 100,000 ways total. Here's the number of ways of not getting what I want. And I do this, what was it? 5 days a week, 52 weeks a year, 20 years. Right? There's a probability you don't get what you want. You know, you miss every single time. So finally, at the end, you can take that out if you want to. And this is basically 100%. So notice, right? 100,000 minus 449 over 100,000, that's like 0.9999 something, right? But if you take 0.999 and raise it to a gigantic power, it gets smaller and smaller and smaller. You know? So the higher this power is, the lower you're making this fraction. So then if this is close to 0, 1 minus is close to 1. So that's how you can approach problems like this. So if you have anything that happens once right here, and that happens once, and you want to repeat it a bunch of times, you can do this sort of count setup, multiplication rule-wise, and then do a complement at the end. Okay, so are there other questions you guys want to go over on the homework? Anything bothering you? Go ahead. 13. Share this real quick in 13. Oh, this is from the book? Okay. Yeah, so let me just show you that real quick. I guess I gotta get the book up. Okay. So what this wanted you to do was to just sort of put the birthday problem in its most general framework. So you, instead of having n people, you have n balls being dropped into compartments. Those represent like birthdays. So like January 1st is a compartment, January 2nd a compartment, so on, right? So in part A, they want you to just explain why this general formula is true. And notice it's the same, it's the exact same thing we did in class, except instead of a C, we had a 365. And we still had our n there for a number of people, you know. So they just want you to point out that, like, oh, in the bottom, if you're like assigning people birthdays or dropping balls in compartments, in the bottom you have complete freedom there, the C to the N, right? So the first ball can go in any of the C compartments, the second ball any of the C compartments, and so on, right? But now, if you're gonna miss up top, right? So you're not gonna get a birthday hit. Everybody's different. The first person, the first ball has C compartments that can be dropped into, but then the next one has one fewer options because you can't repeat. And so on all the way down the line. So they just want you to explain that, like, that's the same thing as the birthday problem, just in general. So again, we had a 365 in for C. So they're saying, well, you could just replace that 365 with any other number of birthdays, you know. Then part B, the instruction said you can just take as a given. You don't have to prove that if you don't want to. They can just accept it and move on to part C. So if you want to prove it and get some bonus, it has a little hint, you know, but anyway. So this, by the way, is the formula we had in class on the handout, you know, so I just gave that to you. So if you take that as a given, then in part C, they want you to think about if you're gonna have a 50% chance of getting a match, so like you're in the room with all these people, probability of coin flip, the two people get a hit, they claim that that number of people will be approximately 1.18 times the square root of the number of birthdays there are, number of possible birthdays. So for part C, really all you're supposed to do is you're supposed to say, okay, I take this as a given, this guy here, and then using the fact that I now know the probability is supposed to be 50%, explain why this is true. Okay. So really all you're supposed to do is slot in a 0.5 there, because this is the probability. You can slot in a 0.5 there and then see what the consequences are. So I can show you that real quick. You slot in a 0.5. I'm just going to ask Wolfram to isolate n for me inside this. So this equation, right, you guys could solve using natural logs, but, you know. Anyway, so Wolfram solves it, and it gives you this guy here. Right, this n equals. So this doesn't look quite like this, but it's all approximation, you know. So if you fiddle with it, you can get that. So for example, n represents a number of people. So if you just shave off that half a person right there, it doesn't really change the answer that much, right? So you can shave off that half a person, and you may as well, because this thing here doesn't have a plus half, right? You can also, when you're under a square root, adding a 1 doesn't change things very much because roots are pretty slow growing, right? So you can also just forget about that plus 1, you know? If you do that, then it turns out that root 5.5, whatever this is, right, times a half, that's where they get that 1.18 from. So again, it was really just a matter of you slot in a 0.5 right here, see what the consequence is for n, and you can just kind of fiddle with this, right? Just be like, oh, I don't like having a plus 0.5. I don't want half a person. A plus 1 under a square root makes no difference in approximation, right? So that's how you get that. So then you can conclude by saying, okay, well, if there were 365 birthdays, and there are for the standard problem, right? You can do 1.18 times square root 365. There's your 23 people, right? That's the result we got. So anyway, this formula really is, I mean, it's not like on the nose, but it's a pretty good approximation of what you get from this unwieldy fraction up here, you know. Anyway, so the problem looks harder than it was, really, right? Especially if you can take part B as a given, you know. Okay, so I'll have those homeworks graded by next Wednesday. So if anything comes up when I'm grading, we can talk about it next week. As I said at the beginning of the week, right, especially these coincidence problems, those take some getting used to, right? So that's why the homework is due on Friday, not due on Wednesday, give you some extra time. Okay, so let's now move on to section 3.3. So 3.3, I think you'll find is kind of a conceptual break from 3.1, just like 3.2 was. So 3.1 with the birthday problem, usually students have the most trouble with that from chapter 3. Coupon collecting, the underlying concept is pretty subtle, right? With that sum of random variables, but we're not going to use that very heavily. So usually students don't have much trouble with section 3.2. Section 3.2 is, section 3.3 is kind of like 3.2, and that normally this section goes fairly smoothly, at least in terms of the homework. So recall what chapter 3 is doing. It's trying to give you sort of like a getting your feet wet introduction to various classical tools, like sum of random variables, like complements, things like this, using fundamental classical examples. So today, the tool they want to introduce you to is a chance tree. And this is something you've seen if you did any probability in high school or something, right? So for many of you, this will be a review. And the example they're going to use is the casino game Craps. And unlike other games like, say, Chuck-a-Luck or Sick-Bo or something, right? You can, of course, go to a casino right now and play this, right? So we're going to figure out the probability of winning at Craps using a chance tree. And the thing about Craps, as we'll see in a second, it's on its face, seems like a very hard game to analyze because in principle, it could go on forever, you know? So the question is, how do you calculate the win probability of a game that could in principle go on forever? So that's what we'll do today. Okay, so before we do that, let me just show you what, if you took any probability or stats in high school, what a chance tree would be introduced to you as. So let's forget about crafts for a second. And let me just focus on a much simpler problem. Okay, so here's a problem. You flip a coin twice. What's the probability you get exactly one head? Okay, that's a fairly straightforward question, right? So of course, if you wanted to answer this using chapter 2, you'd be like, all right, well, there's only like 4 things that could happen, right? You know? Do I agree with that? They say, well, 2 outcomes are what I care about out of the 4 possible, so I have, right? Everybody okay with that? Okay. So you don't need any fancy machinery here to answer this question, but it is a nice little intro to what a chance tree is. So a chance tree, at its foundation, it just shows you everything that could happen. And so notice in an experiment like this, where you flip and then flip again, right? It's sort of sequential, right? You do something to do something else. So a chance tree helps you visualize that. Okay, so initially, you've done nothing. And from nothing, you either get a heads or a tails, right? I agree with that. So there's like stage 1. Then stage 2, like from a head, you either get another head. From a tail, you get another head or tail. And so this experiment has 4 outcomes, and you get the 4 outcomes from the 4 branches of this tree. So you can go all the way across the top, you can go up, down, down, up, down, down. Okay, so starting here and walking all the way to the edge of the tree gives you a possible outcome of the experiment. You okay with that? Okay, so among other things, it shows you all possibilities of what you're doing. Notice though, there's no probabilities here, right? So where are the chances, right? So once you draw this, you then decorate each of the individual edges of the tree with probabilities. So you ask yourself, okay, there's a branching right here, right? I can go up or down. What's the probability of taking the top branch? It's just a half, right? Right? And in this chance tree, everything is a half everywhere, right? So you decorate every single individual branch with the probability of taking that step. So like if you're right here, right? If you're at a tail, what's the probability of then getting a heads off of that? It's a half, you know? So now to answer this question using this tree, you do the following. You say to yourself, okay, what do I care about? Exactly one head. So then you come in with like a highlighter and you take every walk in the tree that corresponds to an outcome like that. There are 2 of them. Do I agree with that? So then to get the overall probability, what you do is for each of these walks I took in the pink, as you walk, you just multiply probabilities as you go. So here's a walk from start node to then this stem right there, right? Half, half. Then you add any other branches and multiply as you go down those. So there's another branch like this pink one here, and half, half. So that's how you use a chance tree to answer probability questions. This now shows you everything that could happen, right? And the probabilities of individual steps. So then to get the probability of the overall question you wanted, you plot all possible walks through the tree. Each individual walk has a probability associated with it by just multiplying as you go. And then you add the other branches on top of that. So it's a multiply and then add to the next branch. If there were like a 3rd branch down here somewhere, right? You'd multiply and just tack it onto this. And here you get a quarter plus a quarter is a half. Let me step back and ask, does that make sense? That's how we're going to use this tree with crafts. We're going to set up the tree to plot out everything that could happen. And then the probability, what we care about, we'll just walk, multiplying as we walk, and then when we end, reset, add, walk, multiply as we go, reset, and so on. These things will be especially useful in chapter 8. So the book introduces them now so we get our feet wet. So when we go to chapter 8, we're not starting from scratch. Okay. Sorry, so now let's talk about craps. How many of you have played craps? Only one. Okay. How do you play craps?
I don't know. Real confusing.
Correct. Yes, that's the right answer. So Trent said it's real confusing. He doesn't know. Yeah, so here are the rules. So I guess I should say there are, of course, variants of craps, right? So when somebody says like poker, there's like 30 billion versions of poker, so same thing with craps. So that caveat out of the way, here's like a standard version of craps. So you start by rolling 2 dice and you record the sum. Yeah. Yeah, you could, yeah. But I mean, it depends on what variant you care about, right? Yeah, I mean, there's like Texas Hold'em, there's, I don't know, the standard traditional where you hold the 5 cards. Yeah. Yeah, you could, yeah. But anyway, I mean, so the probability questions will change based on which variant you're studying. So for craps, we'll just study this variant here. This is like the standard one. So if you go into a casino and say, I want to play craps, the probability is high they're doing this. But again, there are other variants. Okay, so you have some like initial dice roll. And if you initially roll a 7 or 11, you just win outright. Okay, so you roll the 2 dice and it's like a 4 and a 3 or a 5 and a 2, you win. 6 and a 5, 5 and 6, you win. If you initially roll a 2, 3, or 12, then you just lose outright. Okay, so there are 5 ways the game can just terminate like immediately. If the sum is 7 or 11, terminates immediately, you win. 2, 3, or 12 terminates immediately and you lose. But suppose you roll something else, like say a 5, right? Then craps goes into a second phase of the game. So what the dealer does is they're like, okay, I see your 5. I'm going to bank that, record that, okay? Then we go into a second phase of the game, and you just keep rolling the dice until you roll your 5 again, right? Your initial roll, you roll that again, in which case you win, or you roll a 7, which now is no longer a win for you. That'll be a loss, okay? So just to make sure we're clear on the rules, let me give you a sample rolls, see what you think about them. If we're not clear on the rules, then nothing we do today makes any sense. Okay, so you're at the craps table. You're Trenton looking very confused at the craps table, right? Let's say your roll is this. Die 1 is a 2, die 2 is a 1. You roll a 2, 1. What happens to you? You lose immediately, right? What if you roll a 4, 3? You just win, That's nice. What if you roll a 4, 4? What happens to you? Okay, so that becomes the point. The point is 8. Okay, so now we record that 8, and now we roll again, right? Suppose our next roll is a 2, 2. Doesn't matter, okay? So in phase 2, you're going to roll the dice until you either see this again, and you win, or you roll a 7 and you lose. So if you roll a 2, 2, it's just like, okay, whatever. Now, what if you roll a 1, 2? Pick up the dice, you roll them again, right? What if you roll a 4, 3? You lose because you rolled the 7 before you got to see your 8 again, right? That'd be a loss. But if you rolled a 4, 4 here, you would win. Okay, so the second phase of the game, I think you'd agree, is kind of complicated, right? It could potentially go on forever, right? Do I agree with that? That's how craps works. So you either win or lose outright, but for most rolls, you go into a second phase where you're trying to redo your first roll before you roll a 7, which is a loss. Okay. So is everybody clear on the rules of the game? Okay, so the first question is, thinking about the win probability here is difficult. Why is that difficult? Yeah, so that's certainly true, right? So there's not really a equal weighting to this game, right? So probably rolling a 2 is different, probably rolling a 7, that's true. That can make the problem hard. Anything else about making this like analyzing this? If I gave this to you right now as homework and said, what's the probability you win at craps today, right? What would be hard about that? Yeah. Yeah, how are you going to deal with this re-rolling thing, right? That, again, could potentially go on forever, you know? How do you deal with that? That seems hard. Do they agree with that? Yeah. So basically, a chance tree will let us do it. So it's a little subtle, so we're going to walk through it pretty carefully here. But first, let me just show you the chance tree for this game. The chance tree is too big for me to fit on one page, but you get the idea. So right here at the start node here, that's when nothing has happened, right? So you could initially roll a 2, that's a loss, right? Initially roll a 3, that's a loss. You could then roll a 4, which is not an initial loss or win, right? Now you go into phase 2. After rolling that 4, now you can either win, lose, or I guess there's a tie option, right? Do they agree with that? You're just sitting there forever at Isle of Capri, right? In purgatory, right? Like Sisyphus or something, always rolling dice, never losing or winning. And same thing with 5, right? You can just roll a 5 initially, that's your point now. Now you got to go into the second phase. A 5 before a 7 now is a win, 7 before 5 is a loss. That's how the game terminates, or a tie. And so on, right? You just keep this going all the way down to 12. Is it okay with that? Now, what we have to do today is think about our win probability. To calculate that, we'd have to be able to decorate all these branches, right, with probabilities, wouldn't we? Do you agree with that? So if I knew what this decoration was here, for you guys on Zoom, if I knew what this decoration was here, and then also this one here, and same thing for this, same thing for this, then I'd have the information I need. Because to calculate the probability overall, like here's a walk where I win, right? 4 and then 4 again, that's a win branch. 5 and then 5 again, that's a win branch. 6 and then 6 again, a win branch. 7 just outright, it's a win branch, right? If I can just decorate all these things, I can then do the thing I did with the 2 heads or the 1 heads, right? I multiply all the way to the end and then add. Multiply, add, all the way down. So the challenge of today is, how do you decorate these branches? And some of these branches, by the way, are not so hard to decorate. Like, if you want to put a decoration on this edge here, what's that probability, or how would you get it? Yeah, so we've built the chart, the 6x6 chart before, right? The 36 ways to roll a dice initially. As you say, only one way to get it, some of 2, right? So we know pretty quickly this is 1 out of 36. So basically, any of these initial branches we can get pretty quickly, right? Does everybody agree with that? So I'm going to start putting a few of them on the board. Again, the overall tree is big. We don't need the overall tree, though. Now, in particular, if we care about win probability, those branches that end in loss are of no consequence to us, right? Because we're not walking those paths. So let me put a few win branches on. So I could get a 4, and then 4 before 7. That's a win. I can also get a 4, like 7 before 4. 5, 5 before 7. 7 before 5. There's also a 6 branch. Let me ignore that for a second. 7 and 11 were the other ones. That sort of stand out. Okay, so there's far more branches here, right? Okay, let me just ask you. So rolling a 2 was probably 1 out of 36, right? What's the probability of rolling a 4? Sum of 4. 3 of them, right? You can do 2, 2, 1, 3, 3, 1, right? So again, if we want to put that 6x6 chart on the screen, we can. And for 5, like this, 7 is 6 out of 36. By the time you get to 11, it's only 5, 6, 6, 5, right? So these probabilities are going up, and then they sort of peak at 7, and then down here. So in terms of winning, the winning walks we have, we could walk like this. We could walk like this. We could walk like this and just stop. So there's a plus 6 out of 36 going on. We could walk like this and just stop. So there's a plus 2 out of 36 going on. So basically, right, we multiply these as we go, then add, multiply, but this multiplication is just length 1, right, and so on. So this is the challenge for us, right? If we knew what to decorate that branch with, and so on, we could be done here, right? So any questions on the basic framework here? Okay. So our challenge is sort of set before us. And it seems like it would be pretty hard to do, right? So if I just came to you and I said, look, I want you to roll 2 dice. And you're going to have to maybe roll them hundreds of times. I don't know. What's the probability that you see a 4 before seeing a 7? Like, I don't know, man. That seems pretty hard, right? Would I agree with that? Okay, so let's just see how to analyze that. And the nice thing about this is that, again, there's some nice Calc 2 up in your face, right? You guys like Calc 2? Well, you're going to learn to like Calc 2. Actually, this is probably the last time I'll use infinite summations like this. So I guess if you don't like it, you got one more day of it. Oh, no water. All right. Okay, so let me just provide some notation here. So let's let AK denote the event that we're in the second phase. The first K-1 rolls are neither 4 nor 7. So I'm going to focus on 4 and 7 for a second. So this top branch up here, right? 4, 4, 7. Okay, so you rolled neither a 4 nor 7, but then on the kth roll, finally you get your 4. I claim the probability of such a thing happening is this expression right here. You believe that? Sure. Why do you believe that? Okay, very good. So if you couldn't hear Trent, he was saying, well, look, 1 is the overall space, right? Everything is at the 1. So from 1, if you're not going to roll a 4, you got to take 3 out of 36 out of it, right? So here's no 4, right? But you also got to avoid 7s, don't you, right? Probably a 7 is 6 out of 36. So this right here is the probability of seeing neither a 7 nor a 4. You can see anything else, right? You guys agree with that? And then Trenton said, and then you got to repeat that K-1 times. So imagine going through the chancery, right? Miss, 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 miss. Chancery, you're allowed to multiply your way down the line, right? So you miss K-1 time. So I miss in the first one, miss in the second one, miss in the third one, finally. But then finally on the kth one, what happens to me? I get my 4, right? So there's one final probability there at the end of getting a 4. Let me pausing and ask. This is basically the only key observation of this section, really. Now, if you replace 4 with a 5, right? If this instead of 4 were a 5, that of course changed this and changed this, but the logic is the same. So what do you guys think about this? Anything unclear about that expression there? I mean, do you want to work this out for specific K values? Like what if K is 5? Do you want to see that? Yeah, so K is like on the kth roll, I finally get my 4. But before that, I missed 4s and 7s. So the process had to keep going. So before that 4, I also didn't get a 7 because that would make me lose, you know. So this is like the probability I win on my kth roll, you know. First K-1 I miss, and the process keeps going. So for example, if K were 1, right? If K were 1, that'd be like, oh, I just roll and I get my 4 immediately, you know. Then this term here just becomes a 1, like it's not even there. And there's my probability of getting my 4. But what if I get my 4 on my second roll? That must mean I missed a 4 and 7 on my first roll, right? So then I just have that 1 minus 3 minus 6 to the 1 power, right? There's my 1 miss. Okay, so this question here is, right, where'd that come from doesn't make sense. So that's what I'm asking you right now. Because if you understand that, then we can basically finish off the analysis. What do you guys think? Okay, so I claim this. I claim the probability of rolling a 4, 4, 7 is this sum. Why is that? And in particular, we all said we agreed with this, right? Where is this sum coming from? How does it relate to that formula up top? Okay, good. So this is just this first 3 out of 36, Trent says, that's just rolling a 4, like right now, right? Yeah, so maybe it'd be easier if these were swapped in order. Multiplication doesn't care, right? But this is like, oh, I missed once, right? Everybody see that? This is 36 over 36, but you take out the 6, you take out the 3, right? That's just this number here. So this is like you get your 4 immediately. This is like you get your 4 after a single miss, 4 after 2 misses, right? You get your 4 after 3 misses, and so on off to infinity, right? That could happen as many times as you want. So here's probably getting your 4, and then I equals 0. I is clicking through all the possible waiting periods, right? So you get your 4. So if I were 1,000,000, that means you had to wait like 1,000,000 times, right? Before you finally got your 4. Okay, so let me just ask again, is this clear? This is the probability you get your 4 before 7, right? And again, it might take a while, right? That's why I keep going on forever. Yeah. 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 Yeah, okay. So sorry, if you guys on Zoom, the question was basically, why would you multiply by the 3 over 36 at the end, right? And the reason is because if you're going to do k rolls, so again, maybe it's easier just to put an example up. Okay. All right, so suppose I said to you, Zach, I want to know the probability you get your 4 on like your third roll, okay? So in order to make it to that third roll, you have to miss twice. So here's the probability of a miss. Then you got to miss again, right? So first miss, second miss, but then on the third roll, you're supposed to hit. You're supposed to get your roll. And the probability of hitting on that third roll is like that. This is the probability of 4. So this here, this is probability no 4, 7. Probability no 4, 7. And finally, probability of 4 right here. So those 3 things must happen. So if you don't have this thing at the end, it's kind of like you're saying, oh, on my third roll, I'm like guaranteed somehow to get a 4. But on that third roll, there's no guarantee of getting a 4. You know, you have 3 out of 36 chances of getting that 4. What you've said is basically correct. Basically, we're about to see that the probability the game goes on forever is 0, actually. Yeah. So in this chance tree here, oops. In this chance tree here, there's this third branch, never roll a 4 or 7. That'll turn out to be 0, is what you decorate that with. So there is no probability of a tie, really. Which I guess is good news, right? It means you can eventually leave the casino. Right? Yeah, right. Yeah, so casinos are always finding ways to trick things up, right? So like roulette, you know, there's like all sorts of betting patterns you can place that aren't just what we did in class, you know. And you're just surrounding, again, the underlying game is like, I pay them $1, they give me 98 cents back. Something, right? So all sorts of ways you can dress up that game. Yeah. Same thing with craps. Okay, so this sum here should look familiar to you from Calc 2, right? Do you remember that? Do you know what kind of sum this is? No. You got a number here less than 1 being raised to a power.
I'm going to send Dr. Rafizi an email after this and say, your students don't remember what geometric series are. Okay, now, of course, it doesn't matter if you remember that's a geometric series or not, right? Because what you're going to do if you see that is you go here, sum. Let me show you how to type a sum into Wolfram. You give it your formula. So our formula is, there you go, 27 over 36 to the I, and then you can just tell it from I equals 0 to infinity. You can just tell it that in English. So you're saying, well, from sum formula from I equals 0 to infinity, and it'll do, of course, the geometric series for you. What? Oh, yeah, sorry. Okay. Yeah, so this sum, right, is just 4, right? Okay. But of course, it was multiplied by 3 out of 36. So let me just put that on there. So we have the full probability here. 3 over 36 times that sum. And it gives us a third. So this probability here, again, Calc 2 is what's under the hood here, gives you a probability of a third. And that's actually what this fraction is here. There's another way of writing a third. Okay, so again, here's another Calc 2 application for you, right? Here's an infinite series that can answer a question that seems on the surface really hard, right? Again, if I just ask you cold, here's 2 dice, roll them until you get a 4. But if you get a 7 first, you have to stop rolling. What's the probability you get your 4, right? That seems hard. But you can think of that process as modeled by this infinite series, and suddenly Calc 2 kicks in, and it gives you an answer here of a third. That's what this fraction is down here. I've just written it suggestively because notice if you write the number of third, the fraction of third like this, here's your probability of a 4 up here, and then down below is your probability of a 4 and probability of a 7. So that turns out to always be true. Nothing special about 4 and 7, as I say here, right? So if you're just ever asked, probability of rolling I before J, you can set up this exact infinite series again if you want to, but it'll just turn out to be like this. Probability of rolling the first guy divided by the sum of the 2 probabilities. Yeah. So as Trent says, rolling a 7 is the most likely outcome, right? And they're giving you that for the first roll, right? If you roll a 7 initially, you win. Yeah. Yes. Now you move into phase 2, and now it's weighted for them, right? Yeah. So the question is, like, how does that balance out? Because you have this sort of nice path to victory initially, so that's in your favor. But if you make it to phase 2, it's in their favor. How does that balance out? Okay, so here it is. Here's the eventual sum we get. So let me again draw the tree real quick, and then we'll be done with this. Just to make sure we all understand where the sum is coming from. Okay, so inside that tree, let me show you all the ways we can win. We could roll a 4 initially. That probably is 3 out of 36. And then we could roll a 4 before a 7. And we have this nice formula now that says, oh, probability of 447 is like this. 3 out of 36 divided by 3 out of 36, 6 over 36. Okay, or we can initially roll a 5. I'm probably rolling 5 is 4 out of 36 because it's like 4, 1, 1, 4, 2, 3, 3, 2, right? And now here, it's 5 before 7. Now you just replace 3 out of 36s. Okay, so what's the probability you win like this, where you initially roll a 4 and then you get your 4 again before getting a 7? That probability you multiply down the line, right? 3 out of 36 times this fraction. And then what's the probability you win this way? 4 out of 36 times that fraction. So on, right? So that's where this big ol' summation is coming from down in the answer. Share it one more time. Okay, so here's your probability of rolling 4 initially, and then there's that a third. That's what this guy is here up top. Here's your probability of rolling a 5 initially, and if you do this fraction with 4 out of 36 in it, you'll get 4/10. Here's 5 initially, and then there's the 5 fraction before 7. And then right here, this is just a probability you roll a 7 straight up, right? If you roll a 7 straight up, it just terminates. You don't go into phase 2. So there's no multiplication there. And then here's 8 first, 9 first, 10 first. Here's your 11, right? If you rolled 11 up front, just you're done. So if you add all those things up, all these branches in the tree, you end up with a probability very close to 50%, all right? But not quite. So it's just slightly biased against you. Okay, so again, the big takeaway from this is a chance tree is a nice way to visualize what's happening in this game. And then if you can just decorate these branches with the corresponding probabilities, and those probabilities might be hard to get. You know, they might involve geometric series from Calc 2, you know. But you decorate the branches of this tree, then you can multiply down the line and then click add, multiply 5, 5, click add. There's a 6, 6 branch. Then again, just 7 stops, right? No phase 2 for 7, and so on. Okay, so questions or comments about any of this analysis here? Okay, so we have time for you to try at least one homework problem. This also is a takeaway from the homework. If you are doing a straight up dice rolling game, like a craps or a variant of craps, you can just grab this if you want to. So speaking of that, let me bring up a variant from the homework. This is now new homework, right? Which of these PDFs? Not that. Yeah, right. This is the right PDF. Okay, so try this number 5. If we have time, we'll move on to number 6. Let's see if we can do number 5 before we go.